Greetings. In this video I want to tell you about a method to find optimal paths between different states. It's useful in a variety of physical systems or situations, but of course I'm going to frame it in the context of polymer physics. If you've seen other videos on this channel, you probably know that polymers can form a variety of stable or metastable structures, but it's often useful to understand how one structure can turn into another. This can happen through some kind of instability, like spinodal decomposition, where the initial state becomes unstable and gives way to the final state, as shown here. On the other hand, it could happen that the initial state is metastable, like this modulated disordered phase that's just hanging around for a while until a droplet of the lamellar phase happens to randomly appear and happens to be large enough to grow. You can see it starting to appear at the top of the simulation box, and now it's growing to engulf the system. We can picture this in terms of the free energy landscape, here shown as a function of some abstract reaction coordinate. It fluctuates around this local minimum for a while until the fluctuation is large enough, then it goes over this hump and falls down into the deeper free energy minimum. A simple description of this is available from classical nucleation theory. Consider a droplet of the lamellar phase in a bulk of the disordered phase. The disordered phase has some free energy density, Fd, similarly for the lamellar phase, Fl, and thus some difference sigma. Sigma acts like a pressure. If it's positive, the system lowers its free energy by converting disorder into lamellar and growing the droplet. There's also a surface tension, gamma. There's some structure to the interface between the lamellar phase and the disordered phase. We can immediately see that the free energy of this structure has to be larger than either of the phases. If it wasn't, well, the system would prefer to be in that state rather than either of the metastable states, so this would be the metastable structure. So the surface has to be unfavorable and gamma is positive. We can therefore write the free energy as a sum of the surface term that varies with the length of the droplet squared, and a volume term that varies with the length scale cubed. For a spherical droplet, these terms are proportional to the usual surface area and volume of a sphere. The droplet that we just saw was clearly not spherical. This is due to a dependence of the surface tension on the angle at which the lamellar phase meets the disordered phase. A full description of this is beyond the scope of this video, but if you're curious, I recommend looking up the Wolf construction. If we plot this free energy, we get a shape like this. There's an initial increase due to the positive r squared term, so the droplet can lower its free energy by shrinking. This is followed by a decrease in the free energy at large r, so the droplet grows. In between, there's some critical size for the droplet, and this gives the barrier to the nucleation. A similar description applies to the nucleation of a pore from a membrane at fixed tension. This time we have a line tension around the pore, and a membrane tension acting like a pressure pulling it outwards. Of course, real life is rarely so simple. For one thing, classical nucleation theory works well when droplets are large compared to all of the other length scales of interest. But what about if the critical size for a droplet is comparable to the size of the modulations for the phase? Or if the pore is close in size to the membrane thickness? And of course, we don't just care about nucleation, there are tons of activated processes for which we don't have a nice reaction coordinate. This makes it impossible to write a simple theory like this. So let's go back to our free energy sketch. I'll make up an order parameter and call it alpha, and I'll label the beginning state alpha equals 0 and the end state as alpha equals 1. And we can try to come up with some parameterization that takes our system through the intermediate alpha values. We can describe the state of the system in terms of the density ρ. Let's assume that the system is incompressible. This allows us to use the concentration of just one monomer type for simplicity, but there are obvious ways to generalize this. I want to emphasize that we can think of this function as a vector in some Hilbert space of configurations. Every point in real space corresponds to a dimension in this Hilbert space, and the projection of the location onto this dimension is the concentration at this point. If you prefer, you can think of the state of the system as a set of ρ values at every point in space, and we can put that set of ρ values into some big list, a column vector. In practice, we discretize ρ onto some kind of grid, so rather than an infinite dimensional vector, we have some finite dimensional vector. Still a lot, though. We might want 100 points in each direction for the system. This leads to 100 cube points, i.e. our state is a vector with 1,000,000 dimensions. Changing the structure is the same as changing the vector in our configuration space, or changing the point in Hilbert space that corresponds to our system. The vector that describes our system is a position vector for a point in this Hilbert space, and changing the system corresponds to moving around that point. Of course, changes to the system are also vectors that move the point from one place to another. This is all a bit abstract, but stick with me, I'll try to make it a bit clearer. Next, recall that the free energy is a function of this concentration, so it's some kind of function defined in our high-dimensional Hilbert space. So if we want to find what our system's likely to do, we can think of how moving in the configuration space changes the free energy. Unfortunately, I was born without the ability to draw graphs in millions of dimensions, so let's think of the system in terms of just 2 dimensions. You can think of this as a system with 2 degrees of freedom, or as a projection of a much higher dimensional system onto 2 degrees of freedom. But now we have a plot of the free energy where the 2 horizontal dimensions shown here correspond to the 2 degrees of freedom that we're considering for our system. So a point in this 2-dimensional space corresponds to the state of a system. There are 2 local minima, and the system will like to hang around close to these minima, basically fluctuating close to this free energy minimum, inside essentially a free energy well. The probability of fluctuating a given distance from a minimum is given by the change in the free energy associated with its fluctuation. A path connecting these 2 states is some curve in configuration space, and the most likely path is the curve that minimizes the free energy along it. This is the key to the string method. We represent the state in some configuration space, and find the path or string through that space that minimizes the free energy. The rest of this video is all about ways of doing that. Just a heads up, I'm going to use the terms string and path through configuration space interchangeably. Typically what we want to do is have some starting string. If you've seen my other videos, you're probably familiar with the idea of starting from some guess for the state that the system wants to be in, and then relaxing this guess into some optimum using some kind of free energy minimization. The principle in the string method is the same, but moving up a dimension. This time, instead of, for example, a 3D spatially dependent configuration, we have a 4D space-time configuration that we want to relax. So to get from this path to this path, we need some optimization method, some way of relaxing the string. If we have a point in configuration space that we want to optimize, we can use any of a variety of relaxation techniques. Popular methods include dynamical relaxation methods, like Model A or Model B dynamics. The details are beyond the scope of this video, but essentially Model A dynamics drives the evolution of the system through the chemical potential, this derivative of the free energy here. It doesn't locally conserve material, and can be thought of as if the system's attached to some kind of reservoir. Model B, on the other hand, drives the evolution by gradients of the chemical potential. These gradients give rise to a current, and the rate of change of the concentration is given by the divergence of the current, thus the Laplacian of the chemical potential. Anyway, the point is that relaxation techniques exist. If we want to relax an entire string, we have to discretize it, and use some technique to relax the entire string as a whole into some local optimum. We define the string as an ordered set of points in configuration space. To calculate the position along the string, we can use the L2 norm to calculate the distance in configuration space between 2 adjacent points, and then just add up the distances along the string to get the total position. Notice that the position is normalized because I still want alpha equals 0 to be at one end of the string, and alpha equals 1 to be the other end. I'll say a bit more about coming up with the initial guess for the string later, but first I'll discuss some methods for relaxing it. You could just relax each of the points individually. Of course, this leads to them all clustering around the local minima, and you get less of a string and more of a pair of configurations with a lot of redundancy. You need some way to keep them together so they don't just separate into distinct minima. One thing that you could do is add a spring potential that keeps them from getting too far apart. So this is the normal Model A evolution equation, and I've added this other potential that depends on the states of the points adjacent on the string. 2 things to note. One is that the new term does not apply to the ends of the string, just the intermediate points. The other is that I've used the convention where the Onsager coefficient is negative. It's often preferred to keep it positive and have a minus sign in front of it. It's just a choice of convention, but it's important to keep track of the minus signs. To understand the string potential, think of it like if I've averaged the state of the system on either side and then subtracted it from the current state. That is, found the difference between the current state and what it would be if I interpolated between these points, and then set up a potential that drives the system towards the average. It effectively sets a potential along the string, pulling the points to be evenly spaced. If you read papers about the string method and you see a discussion of this approach, you'll probably see it derided and given as something that you should never use because it prevents the system from minimizing the free energy. It's not apparent in this simple case because the optimal path is a straight line in configuration space. If, however, we use a more complicated free energy landscape, the effect becomes apparent. It looks like it's going okay at first, but then the tension in the string pulls it up the free energy landscape away from the optimal path. This is not good. The spring potential does have its uses that I'll get back to, but you should not use it as the only or even primary tool to calculate your string. Another approach that does actually work is to relax the system but then interpolate along the path to keep the points equidistant. Given some set of points, they relax as shown on the left, and then they can be fit to some function and then interpolated. To break this down a bit more, this is the usual relaxation equation, so first update like this. Then find the positions of the points along the string. They will in general not be equidistant. We want it so alpha at the ith point is given by I over n minus 1, so we can interpolate along each dimension in configuration space and change the value of rho to the interpolated value. That is, for each point of R, you have a set of points representing rho of alpha. Interpolate them to get your new rho I. You have to be a bit careful with the choice of a nice interpolation function. A cubic spline works well. This method works well, but think of what happens when your string is converged. You pull each point down the hill in a direction parallel to the string, and then pull them back up with interpolation, over and over again. It would be simpler if you just ignored the part of the update that's parallel to the path. This is the next method. We want an update that's purely perpendicular to the path of the string. This is why I emphasize thinking of the state as a vector. We now have to think of projecting this vector onto directions in configuration space. The normal update looks like this. This term is the vector that we add to our state to get the new state. The first step is to calculate this normal update. The next step is to find a vector that's parallel to the string. I've called it tau. It's simply given by the derivative of the state with respect to the position along the string. You could find this using finite difference, but it works better to do the cubic interpolation that I mentioned previously, and then use the derivative from this interpolation. Now we want a unit vector, tau hat. This is obtained by simply normalizing tau. Note for these functions that I've been describing as vectors, things like dot products and absolute values are defined similarly to normal vectors with orthogonal bases. Just replace the product of components with the product of values at a given position, and the summation with an integral. Since in practice these are represented on a grid, really it's still just summation. To find the part of the update that's parallel to the string, first calculate its dot product with tau hat. This gives the magnitude along tau hat. Then multiply it by tau hat. This gives the vector that's parallel to the string with a magnitude that is the size of the component of the update along the string, i.e. this is the part of the update that points parallel to the string. Now just subtract off this parallel part from the update to get the perpendicular part. In practice, you probably want to combine the perpendicular update and the interpolation. The perpendicular update is cleaner, and it gives you direct access to the degree to which your string is converged. But drift in the points, or a non-uniformly distributed initial string, can lead to non-uniformly spaced points, and you don't want that. When you combine these two methods for this complicated free energy landscape, you get something like this. It relaxes nicely into the minimum that you would expect intuitively. I called this landscape complicated, but it's actually much simpler than any non-trivial problem that you would actually want to use the string method for, so you have to be a bit careful. But if you are, you can get pretty cool results. I started off by talking about nucleation, so here's a calculation of the nucleation path for a gyroid phase from the lamellar phase. There are two paths presented, one that goes through the perforated lamellar phase, labeled E, and one that nucleates directly. Note that neither of these free energy curves look like the classical nucleation theory curve. This is not surprising, because the size of the nucleus is not a whole lot bigger than the modulations of the phase, but the string method handles it with no problem. But the string method's applicable to a lot more than just nucleation. This is the pathway that I found for the fission of an inner tube of a pair of membrane tubes. It's quite complicated, and there's no simple reaction coordinate. The free energy barriers are also large enough that I can't just leave a simulation and hope that it fissions at some point. This calculation was only really possible because of the string method. Before I end this video, I want to briefly return to the spring potential approach. As I said, it's not a good way to minimize the free energy because it doesn't minimize the free energy, but it can be good to help you set up a string. Setting up a complicated four-dimensional description of a system can be a little complicated, and the cubic interpolation that I mentioned can be a bit unforgiving of sharp changes in the density. If, for example, I want to insert a stalk between these concentric membrane cylinders, I can just insert it here. But this leads to a sharp increase in rho as a function of alpha at the points where it was inserted. When I do a cubic fit, I get these wiggles around the sharp increase. This might be okay, or the interpolation and derivative calculation might lead to overshooting of the concentration and of the gradient, leading to strange behavior or even numerical instabilities. On a related note, you can think of the separation of your points along the string kind of like another spatial discretization, in that there's some function defined along that domain and you're evolving it in a time-like way. As a result, you get the same kind of stability issues that you get doing any kind of time-like evolution of some spatially dependent system. A full von Neumann stability analysis is way beyond the scope of this video, but the point is, you should be a bit careful with the size of your update and the number of points along the string. As one final warning, the relaxation methods that I've described optimize the string locally, not globally, so you have to be a bit careful with your choice of initial guess for the string. Different initial strings can lead to different paths. My approach is to try anything that I can think of that isn't obviously stupid or obviously unfavorable, and giving it to the cluster and seeing how it relaxes. At first this might seem like not a great approach because of the size of the potential configuration space, but it's actually not that terrible. With the kinds of problems that I usually deal with, structures with the same topology are usually connected by some continuous path through configuration space with a monotonically varying free energy. So a given topology can usually adapt into the optimal geometry. This isn't always the case, but it's a good starting rule of thumb. So once I start off with the right topology, I'm probably okay. If you're using a mean field approach and ignoring fluctuations, strings can get trapped into locally optimal paths, just like states can get trapped into locally optimal states. You can get around this by using a fluctuating model. I've not discussed it here, but the string method is not just for mean field calculations, and can be applied to fluctuating field theories or even particle-based simulations. It's a very versatile method. If you end up using it for anything cool, please drop a comment and let me know. Thanks for listening. I hope this was an interesting exploration of the string method, and I hope it ends up being useful to you.